Okay, so today I am talking about radiative forcings and the human contribution to global warming. So what motivates this idea is kind of the notion that's out there that's pretty popular, and I just kind of thought that this was a good exemplar of that. Donald Trump in the last presidential debate last year kind of exemplified this idea, and that's the idea that like we don't really know what causes global warming, or we don't know to what extent humans are contributing to global warming or climate change. And so the quote here is, the headline, Trump admits greenhouse gases contribute to climate change to an extent. And so this was the quote from the debate. The moderator, Chris Wallace, says, do you believe that human pollution, greenhouse gas emissions, contributes to the global warming of this planet? And Trump said, I think a lot of things do, but I think to an extent, yes. I think to an extent, yes. And so this is something that, kind of the people that are skeptical of the solutions to global warming have kind of moved to. There used to be, like 10 years ago, there was a lot of denial about the climate changing at all. And kind of, people would make a big deal about snowstorms or cold temperatures, or things like that. But I don't see that so much anymore. But I do see this quite a bit still. It's like, okay, it's warming, but we don't really know like what's causing it, and it could be natural, it could be human caused. And within the realm of people talking about solutions for climate change, you also get kind of contradictory information about what's the most important thing that we could do to reduce climate change. And so radiative forcings are a tool that we can use to assess what is the most important thing. How can we compare these different things, these different influences on the climate to each other, and kind of come up with like what should be priority in order to solve climate change. So my learning outcomes today all have to do with this term radiative forcing. The first one is just you should be able to define what a radiative forcing is. I want you to be able to relate it to this previous idea that we talked about last time, the first law of thermodynamics. So how does the first law of thermodynamics relate to this concept of a radiative forcing? Explain why it's useful. I'm not just introducing it to give you something to memorize. It's a useful tool for assessing the causes and solutions to global warming. You should know what the largest radiative forcing is since 1750. So that means like what's the most important contributor to climate change since the Industrial Revolution, and explain why you need climate models to estimate changes in global temperature from known changes in radiative forcings. So that one's maybe a little enigmatic right now, but we'll talk about that. So first I'll just kind of introduce again why this radiative forcing idea is useful. So we've been talking about these different greenhouse gases. We've been talking about carbon dioxide and methane and nitrous oxide, and kind of just saying generically that they all absorb outgoing long-wave radiation, and so then they influence the temperature of global temperature. And so if we want to like compare them, here's kind of a way to compare them. So these are graphs of the concentration in the atmosphere of these three gases from the year 10,000 or 10,000 years ago, 5,000 years ago, 0 years ago, so present. And this is from a kind of a dated report, so up to the year 2005. And so we see, carbon dioxide was around 280 parts per million for a long time, right before the Industrial Revolution, and then spikes up. But if we look at like methane has, instead of parts per million on the y-axis here, we have parts per billion. So methane concentration in the atmosphere is much, much lower than carbon dioxide concentration in the atmosphere. So it's like 700 parts per billion. And if we look at nitrous oxide, like that's even lower. That's like 250 parts per billion. And so the question is, like, how do you compare these things? Like, so they're all spiking up during the Industrial Revolution, but we want to know, what is their influence on climate? And so, it wouldn't be fair necessarily to say like, methane's influence must be much smaller because its concentration in the atmosphere is much, much smaller. It's only measured in parts per billion instead of parts per million. I mean, we already know that, nitrogen and oxygen make up most of the atmosphere, but they have almost no effect on the temperature. So that's not going to be useful. And so the way to compare these is over here on this secondary y-axis, the radiative forcing in watts per square meter. So over here, we can see that CO2 goes 0, 1, and then there'd be a 2 up here, and then methane goes 0, 0.2, 0.4, and nitrous oxide goes 0.1. And so you can get a sense just from that CO2 is going to be more important than methane, more important than nitrous oxide in terms of this measure of radiative forcing. So let's just put this down in words, like what we're doing here. So the radiative forcing is directly related to our first law of thermodynamics. The change in temperature equals energy in minus energy out divided by heat capacity. But we're going to kind of ignore heat capacity. We're going to say heat capacity of the Earth is basically constant. And so we're just focused on this energy imbalance, this energy in minus energy out. And so the radiative forcing is literally just that part of it. It's just the energy imbalance. And it's imposed on the atmosphere. This is kind of an arbitrary part of the definition, and we'll talk about this a little bit more. But it's the idea that like increasing greenhouse gases from fossil fuel burning is something that didn't kind of naturally come about through interactions within the Earth system. It was the way that this framework works is like we impose that on the atmosphere, and so that is part of the definition of a radiative forcing, is that something is imposed upon the atmosphere kind of from the outside. So radiative forcing is a force that causes the Earth's radiative energy budget to change, and thus it causes its temperature to change. So that's on our left-hand side of our equation. And so it's called a radiative forcing. Radiative should be familiar with what we've been talking about, that these components, there's radiation in all these names, right? So radiative refers to the electromagnetic radiation, which defines the global average temperature. And then forcing is the idea that you are pushing that energy budget in one direction or another, kind of related to this imposed on the atmosphere, that you're putting something in the atmosphere, and thus you're pushing this energy balance out of balance and causing it to move in one direction or another in terms of warming or cooling. So this allows us to compare the influences of very different things, things that sound kind of uncomparable at first, and compare them in terms of their influence on global temperature. So that is the first order issue that we're dealing with, is that the global average temperature is increasing. So it's called global warming. So there's all these other concerns and other things going on as well, but like that is the main thing that we're focused on here. And so we want to know what things influence temperature differently and how do they compare to each other. And so the idea here is that you're just converting, instead of like looking at parts per million and parts per billion, you're converting various changes to a common currency. And the common currency is what it does to the energy imbalance. So it's going to be in this unit of watts per square meter, or a change in joules per second, that unit of energy that we talked about. And it's a flow, joules per second per square meter. So just divided by the surface of the planet. And so using that, we can then compare, okay, what's the influence of, let's say, the sun getting brighter to the influence of CO2 increasing. So at first, they would seem kind of uncomparable, where you would say like, okay, the sun has gotten 10% more light and CO2 has increased by X parts per million. And so it's like, how do you compare those two? Well, you convert them both to watts per meter squared in terms of our radiative forcing here, and then you can compare that. And you can then also, of course, compare that example I was just showing with methane versus CO2, or something that seems even more uncomparable, like comparing the influence of replacing forests with farmland. So that's been going on, right? Since the Industrial Revolution, have been replacing forests with farmland, and that affects our energy budget because it changes the albedo, it changes how much light is reflected back to space. You can compare that to increases in CO2 and say which one is bigger, which one has a larger influence on global temperature. So as we saw in our example, positive in math and science and means positive in the number sense, positive numbers, not good. So positive radiative forcings change the energy balance in a way that causes warming. You get a positive number over here for your change in temperature. And negative radiative forcings are the opposite, where you get a negative number here, so you have a negative number here. So your change in temperature is negative, so that's cooling. Our positive radiative forcings cause warming, and our negative radiative forcings cause cooling. So that's our kind of our definition of radiative forcing. And then, I defined it with this first law of thermodynamics that we talked about last time. That is basically just that energy imbalance part of that first law of thermodynamics. And you should kind of already see why it's useful, is that you're just converting things to a common currency so that you can compare them. So currency, it's like similar to the idea of like if you were comparing, trade between countries or something, that like if the United States sends Ford cars to South Korea and South Korea sends Samsung phones to the United States, how would you compare those two things? You wouldn't like weigh the cars and weigh the phones and say, okay, there's the trade imbalance is X pounds or something like that. You convert them to currency or to international dollars, And that's the relevant unit to compare those things for international trade. And for global warming, the relevant unit is watts per square meter. First, let's just put down the main radiative forcings that have occurred since the Industrial Revolution. So this is kind of the culmination of thousands of studies on this, looking at each one of these things individually. And so this is, I've just redrawn here the latest figure that summarizes all of these things from the Intergovernmental Panel on Climate Change report. And so I just redrew it so I can put things on here one at a time. But we have our years here since the Industrial Revolution, so 1750 up to present, and then radiative forcings in watts per meter squared, where negative means it has a cooling influence and positive means it has a warming influence. So first, let's put on these natural ones. So this first one is volcanic eruptions. What do we notice about this? It's pretty spiky. So these are the big ones. So Mount Pinatubo was our last major climate affecting volcanic eruption, or at least global climate affecting. They tend to be these very powerful volcanic eruptions that occur close to the equator and can inject all of this ash and sulfur dioxide into the stratosphere, where it can stay for a long period of time. So you've got this eruption cloud that's like super powerful, super explosive. Here's just a picture of the crater of Mount Pinatubo, where you can imagine this used to be like a full mountain up to the top. This is in the Philippines. And so this is the type of thing, this is what it looks like from space. And so you should be able to tell that is increasing albedo just from looking at that picture, because if it's white, then it's reflecting solar radiation back to your eyes. And if it's covering the ocean with whiteness, then it's replacing a dark surface with a white surface. And so that's just all the more increasing the amount of reflected radiation back to your eyes, which would cause a negative energy imbalance and a cooling of the temperature of the global climate. And so the CO2 thing, volcanoes do release CO2, but it's just tiny. A single volcanic eruption is not affecting the global CO2 concentration, but it does for a period of time, for a couple years, cause there to be enough of this ash or aerosols up in the upper atmosphere that it blocks out the sun and causes cooling on these short time frames. But after a few years, all of that settles out and you're basically you kind of reset back at zero. So these are these short-lived negative radiative forcings. So we're kind of due, we could have a big one anytime, and then we would expect global temperatures to cool a little bit for a few years, but then basically get back to where they were after a few years. Okay, here is solar. Solar is very small. There's almost no long-term trend in the amount of radiation coming from the sun over this time frame. There's been large changes in solar output over very long periods of time, but not over like 100-year periods of time or like hundreds of millions of years. And so there is this kind of little wiggle. There's an 11-year solar cycle where there's kind of more sunspots, and that causes there to be slightly more radiation coming towards the Earth. But you can see it's very small compared to what volcanoes do. And this is just a picture of a satellite monitoring how many sunspots there are. We have very good measurements of what's coming from the sun since the satellite era, since we have satellites just looking directly at the sun and measuring the radiation. And then kind of further back in time, you have to reconstruct that through various means. But this is our best estimate of what the solar output has done over this period of time. So almost no contribution whatsoever to changes in temperature. So solar and volcanic are basically zero over this time frame. Over the whole time frame. Like volcanic is showing that it can affect the temperature over short periods of time, but we're back to like a reset level right now. Okay, this is an interesting one. Anthropogenic aerosols. So this is basically just like air pollution. This is kind of best exemplified by China right now, where if you're on the ground in China during a very bad air quality day, it's dark. If it's dark, that means there's stuff in the atmosphere that's not letting solar radiation in. And so if it's not coming in, it's probably being reflected back to space. So our air pollution, so not like CO2, but like what we consider, air pollution that would like hurt your respiratory system, or things that, come from, it's mostly sulfur dioxide derivatives. And especially in China, it's the sulfur dioxide that comes from coal burning. That is helping us in terms of temperature. It's obviously very bad for human health. And you can see this on the satellite image of mainland China here. Here's Japan and South Korea. And again, it's this color, it's like close to a white color. It's kind of gray here, but it's still showing that is reflecting solar radiation back to space and causing a net cooling of the planet. So this type of very bad air pollution for human health does cause negative radiative forcing, something that would cause cooling by itself. We see that it was kind of bottomed out and is getting closer to zero. It's like it's still negative, but becoming less negative in recent years due to efforts to clean up air pollution. So we can put on here also this is basically land use. So several people mentioned that. So like this idea of deforestation and just the albedo component of that, just the component of changing a dark forest to a lighter ranch land or cropland. It's kind of obvious here that that's making kind of a big difference locally, but globally it's not very big. It's a slight negative radiative forcing, so slight cooling over this time period. Okay, so let's look at our greenhouse gases. So here's nitrous oxide. So basically kind of flat and then a little bit positive radiative forcing recently. So that means that's increasing, right? We're increasing concentrations of a greenhouse gas, so that's going to cause a positive energy imbalance or warming. Here's our methane kind of increasing, and then it's been a little bit steady. Now it's increasing a little bit more recently. So methane is more than nitrous oxide in terms of its influence on temperature. And then here's carbon dioxide. So our three big positive radiative forcings are these greenhouse gases, and carbon dioxide is the largest positive radiative forcing influence. So the largest influence on warming, if you just look at individual gases, is carbon dioxide. And so there's a reason that carbon dioxide gets most of the attention, is that it is most of the problem. So then we can put the total on here. This is the total radiative forcing from all causes over this time period. And so, the total is like, you're just summing all of these, and then you're summing this negative number. And so this kind of gets us to what Donald Trump was talking about, of like, are humans the main contributor to climate change or to the Earth's energy imbalance? And yeah, it's not even close, because the solar and volcanic eruptions are really the only natural forces active on this time frame. And those volcanoes can do stuff for a couple years, but then that effect goes away. And solar hasn't been doing much over that entire time frame. And so the reason that we're up here, the reason that we have a positive energy imbalance of over 2 watts per square meter is 100% due to human emissions of greenhouse gases. And then that's been canceled out a little bit by human air pollution. So this is looking at this like through time, but you can summarize this in terms of over the entire time period. And so what you're seeing here is on your x-axis, you have negative radiative forcings, positive radiative forcings, and then it's just going through these different emitted compounds that humans emit. And you've got natural changes in solar radiation down here. They don't even put volcanoes on there, because volcanoes, can't really cause a long-term radiative forcing, because this is now summed over the entire time period and summarizing that over the entire time period. And so we're seeing the same thing here, that CO2 is the largest bar here, the largest positive bar. Then you have methane second, and then they have, it's basically like a tie between nitrous oxide and CFCs or halocarbons, looking at these black diamonds here. And the way that they're doing this is that they're saying, like, this is kind of showing how complicated this stuff gets, is that when you emit methane, that affects other constituents of the atmosphere. And so it's not just methane, it's the fact that methane causes there to be an increase in ozone. And so it's showing that basically that, like, when you emit methane, part of the warming comes directly from methane, and then part of it comes from the fact that you're increasing ozone, and part of it comes from the fact that you're increasing atmospheric water vapor in the stratosphere. It's just like breaking it down in a different way. But the main point here is just that CO2 is the largest. And then you're also seeing down here the same thing about human produced pollution or aerosols causing a negative radiative forcing, or something that would be cooling by itself. And you can see where these are affecting the energy budget. So all of our greenhouse gases are affecting the energy budget by affecting that long wave radiation component. So mostly reducing the ability of the Earth to emit long wave radiation to space. So here's those greenhouse gases, and then we have our other components that are affecting reflected shortwave radiation or reflected solar radiation. And then just that direct change in the sun is affecting that, or is a representation of how much incoming solar radiation has changed. And in the current report, it's basically sitting right on 0. So that was the answer to our question here. Now, the largest radiative forcing since 1750, CO2. So again, there's a reason that gets the most attention. So when I look on here, got CO2, CH4, there's stuff that people mentioned, but there's also stuff people mentioned in the chat that seem totally legitimate, seem like stuff that we talked about, but are not mentioned on here. And so some examples of that would be clouds, water vapor, changes in ice, like glaciers. So does anyone have an idea why those are not on that diagram? What did we call these before? In my introductory lecture, I talked about how humans were emitting CO2 into the atmosphere, and then that ends up changing a bunch of other things. So this is an important part of the definition of what a radiative forcing is. I have this kind of little caveat here. Radiative forcing, it has to do with this energy imbalance, but it's from something imposed, kind of externally imposed on the atmosphere. So the idea is like the atmosphere is doing its own thing, and humans emitting greenhouse gases, or the sun changing, or a volcanic eruption is imposing something onto the atmosphere. And then if the atmosphere takes that and changes something like clouds, and it's really like the ocean atmosphere land system, if that like it receives that radiative forcing and then it changes something because of that, and especially because of temperature changing, that's not considered a radiative forcing. That's considered a feedback on that initial push. So the radiative forcing is the initial force, the initial push. And then if that causes something else to change, it can still cause the energy budget to change, but that's a feedback. So cloud feedback, water vapor feedback, ice albedo feedback, those are all not part of this radiative forcing framework, or they're not going to be on graphs like this, but they are very important as well. To pick up on that idea of lifetime, so that's really critical for like water vapor, that I think you've read in a couple of your FAQs that water vapor is the most important greenhouse gas. I think it's kind of weird to say that in the first place, because it's like what you have to like define what important means. It's kind of weird to just leave that hanging, like the most important in terms of what. But what they mean there is that water vapor is contributing the most to the current greenhouse effect. But water vapor depends on temperature. So like if we and humans do emit a bunch of water vapor all the time, there's a bunch of water vapor coming out of all of our smokestacks, and we're respiring water vapor. But water vapor does not accumulate in the atmosphere because of emissions. It basically, water vapor depends on the temperature of the atmosphere. So if CO2 increases, then the temperature gets warmer and the atmosphere can hold more water vapor. But if you just put water vapor in the atmosphere rains it out right away. It says, the water vapor is not going to last in the atmosphere long enough to actually increase temperatures. It just rains out. You need something like CO2 that just accumulates in the atmosphere and causes long-term temperature change to get that water vapor to change. So that's kind of part of why they're defined separately like that. So clouds, water vapor, other things people mentioned were like melting permafrost, decreasing glaciers. So anything that's kind of the effect from an increase in temperature does not get put into the radiative forcing category, it gets put into the feedback category. And so in order to quantify those feedbacks, we usually use mathematical climate models to do that. Mathematical climate models can be very, very simple. They can be run in Excel, or honestly, you could just take this equation. This is basically this first law of thermodynamics rewritten. You could take that and do some hand calculations on a piece of paper, or do it in Excel. And that would be a mathematical climate model. This calculates the temperature, the global average temperature, based on radiative forcings, feedbacks, and a change in temperature. So they can be very simple, or the more famous kind are the super complex global climate models, which are basically computer programs that are millions of lines of code and try to simulate just as many processes as you can think of. So all of the clouds, all of the motion of the atmosphere, a bunch of chemistry, a bunch of changes in vegetation. Now there's just kind of more and more processes being added to these things, and the idea is you want to understand how all of these things interact. And so then if you change the temperature, how do clouds change, and then how does that affect the water vapor in this location, and how does that affect precipitation, and so then that's going to affect the aerosols coming from a desert and all this stuff. But those are all considered feedbacks that would affect the energy budget, but are not considered radiative forcings. But if we want to get at this change in temperature, if we want to scientifically know the causes of the changes in temperature, we don't just want radiative forcing on here. We need to consider all the feedbacks. And so that's why we do use these complex climate models that try to simulate clouds and simulate the ice and simulate the water vapor and simulate everything else that's going on. So then they are including as many feedback processes as they can. And by the way, this is just a chart of those feedbacks if you're interested in them, whether they're positive or negative. This top part is the most important. And so it's showing that we have negative feedbacks overall. The total is negative. That means that the Earth's climate is fundamentally stable and does not just run away like a snowball where you push it a little bit and then it's unstoppable. It has to have fundamentally negative feedbacks or overall negative feedbacks for it to be stable. And the reason mostly that it has overall negative feedback is this Stefan-Boltzmann law, where warmer objects emit exponentially more radiation, and they call that the Planck response here. So there's just different terminology, but that's our main negative feedback. And then we have water vapor as a positive feedback, melting ice is a positive feedback. Changes in clouds, our error bar overlaps with 0. So it's possible that it's negative, but our best estimate is that it's positive now in this most recent report. But yeah, so if we want, instead of looking at radiative forcings, we want to actually look at temperature. We need these models to be calculating all of these feedbacks. And so this is what, a similar exercise to what I just showed with radiative forcings, but with temperature and using these climate models, that this is, again, this is, it's hand drawn here, but it's from this AR6 frequently asked questions figure 1. So this is what observations look like from 1850 to 2020 in terms of global average surface temperature. And then we can put on here with climate models what we think the temperature should have or would have done if we kind of just put certain radiative forcings in at a time. So what if we just put the natural radiative forcings into a climate model? What would that look like? What do we think temperature would have done over this time period? And so that's what that looks like. That there's basically no long-term increase because there's no long-term increase in the sun. You get some decreases in temperature over short periods of time because of those volcanic eruptions, but that's it. So basically the signal of climate change emerged from the envelope of natural variability, the range of possible temperatures in the 70s or early 80s, that we started seeing global temperatures that were basically impossible if only natural influences were acting on the temperature. And then we can put like what would have happened if just anthropogenic aerosols were emitted, so no increases in greenhouse gases, but only increases in this like air pollution. Then we should have seen a cooling over that time period. And then if we put like just greenhouse gases into the models, that's what the temperature should have done. So we should have seen more warming than we've actually seen. But if you put all of these together, if you put the greenhouse gases into the models as a radiative forcing, and you put the aerosols into the models as a radiative forcing, and you put the natural influences in, then you get something like this. You get an estimate from climate models that encloses the observations. So that's showing that the models are basically capable of reproducing observations. So it looks something like this, that the observations are within that realm. And we would never expect actually the models to be able to get all of these wiggles, because that just kind of comes about randomly. And so the models, because of the butterfly effect, just cannot possibly capture those. But if observations are within this envelope, then we basically think that we understand all of the components that are responsible for the various changes in temperature that we see. And so this is just another way of saying that same story, that increases in greenhouse gases are totally responsible for the warming that we've seen since the Industrial Revolution. And so going back to Trump's statement about to some extent, the science says that it's not to some extent, it's 100% of the warming that we've seen is due to human activity. So this last one, I think, is the hardest one. Explain why you need climate models to estimate changes in global temperature from known changes in radiative forcings. It's essentially this notion that the climate models don't predict radiative forcings. You put the radiative forcings into the climate models, because in order for them to predict radiative forcings, they would have to like predict human behavior. We'd have to have some model that said, oh, in 1750 we calculate that's when the Industrial Revolution would happen. That's impossible to do. So you give the model the changes in greenhouse gases, the changes in radiative forcings, and the model then calculates what should happen to clouds, what should happen to greenhouse, or to water vapor, and what should happen to ice, and then that is what's necessary in order to actually calculate the temperature change, in order to get graphs like this where you have temperature over here. And so in order to convert those radiative forcings to temperature, you need something that's going to calculate those changes in feedbacks and to get the full influence of the energy imbalance on global temperature. And so that's what we use. We use climate models to do that.